Okay. So good afternoon, good morning, everybody. Class is live streaming. I think I don't need to give any links to anybody. By now, everybody knows where to get the latest, watch the latest stream on my YouTube channel. So right. So okay. So I just wanted to mention that in the quiz, many people, when I had given you this one problem. Right, an comma a dagger to calculate this. One second, my internet is giving me some issues. Okay, so it's updating a little bit slowly. Okay, can you see it now?
Yes, sir.
Yes, sir.
Yes, sir.
But I can't really conduct class. So this is okay. One second, I'll be right back. Okay, never mind. Yeah, my internet is just giving me too much trouble. Okay, so let's see. So for this, you know, how do you prove this, right? So many people, they said, oh, we have some identity, right? We have some identity that apparently that if you do this, this is equal to d of an by dA or something like this is equal to NaN minus 1, right? But the question is, can you prove this identity, right? So if you can't prove the identity, then you don't really get any marks, because the whole point is that you should be able to do the calculation. So in many cases, I've still given some marks, like half a mark here or 1 mark maybe. Okay. Then the question is that, okay, well, then it's like, well, what is this quantity? And it's like, okay, well, now the question is, why is this true? Can anybody tell me why this should be the case? That let's say this is true. If this is true, then why is the second line also true? See, this is very simple, right? I mean, if you don't know this, then like, I mean, half a mark, 1 mark, really anything I give is too much, right? So this is the point I'm trying to make. You should know I mean, so this is true for any function, actually, any function of A, as long as that function can be expanded in a Taylor series. Right, exactly. Thanks, Chinmay. Okay. All right. So let's talk about a new problem today. We have discussed, we have talked about 1D infinite potential well. We have talked about harmonic oscillator. right? One of the things we need to talk about is finite potential well in 1D. We'll talk about that later. So today we'll talk about 2D infinite potential well. And along with this 2D potential well, there is a new concept called density of states. So it's important to understand this concept. This is a very important concept for this we'll do later, and this is for today. Okay. So what is the two-dimensional potential well, right? Well, as the wording says, it is a problem in two spatial dimensions. Right? So you have two spatial dimensions, x and y, and a particle is moving around in this space. Right? So if I write down a wave function, right, it will be a function of two coordinates, x and y, right? Again, when I say wave function, I mean the quantity psi for all values of x and y, okay? Not for one value of x and y. So this is a wave function. This lives in the Hilbert space, right? So a better way to write it is like this. Psi is an element of the Hilbert space, and such that it is a map from R2 to C. Right? What is this space? This whole space is R2, right? So the state is a map from R2 to complex numbers, right? For each point of R2, psi tells you what the corresponding value of, psi x of y is the corresponding complex number. So this is your state, okay? And then this state, again, if we write it in terms of, we can again define these position eigenstates, right? But now our position eigenstates should be of how many types? There should be two types of position eigenstates, right? Ket x and ket y. So what is ket x again, right? It's the eigenstate of the position operator. What is ket y? The eigenstate of the y position operator. And also it's very important to keep in mind that if you look at this is the Poisson bracket, okay? So we have talked about the Poisson bracket before, right? And I hope that you have learned about it in classical mechanics. Has it been covered in classical mechanics?
Not yet.
Not yet, okay. Have you studied it in your undergraduate?
Not yet.
Huh?
No,
In undergraduate, is Poisson bracket introduced to you?
No, sir.
Hamiltonian mechanics, Lagrangian mechanics?
Lagrangian
Okay.
a little bit, sir, but not in detail.
Not properly. Oh, okay. So the Poisson bracket is 0, which implies that the commutator of the operators, right? So these are some classical functions, x and y. These are your classical values, and the corresponding operators are x hat and y hat. And the commutator of these is 0. Okay. So this is true, right? But if you take, for example, x comma px, that is not 0, right? Or y comma py, that is also not 0. So and if you take px comma py, that will be 0. So how many operators do you have on this set of states on yours? You have these 4 basic operators, right? These are the 4, like you will call them elementary operators for position
Sir,
and momentum. Yes.
sir, if we take x py, then also it is 0.
What?
X py.
Yes. Absolutely. You're right. If you take x and py, that is also 0. Yeah. And y and px, that is also 0. Okay. And right. So this is your 4. You can call these your quote unquote elementary operators. Right. So we will build all the other operators out of these. Now, so given some set of operators, so let's say you have let's say some set of operators, okay? O of I, where I goes from 1 to some value n, okay? We don't know what n is some number, right? It's a number of operators. Given such set of operators which act on our Hilbert space, right? So this curly H is the Hilbert space, it's a set of state vectors, right? Okay. So this is called a complete set of commuting operators, CSCO, right? So given a set of operators, so we want to find out in general, like how to write down. So we find out what is the maximal set of commuting operators. What do we mean by maximal set? So that means that it is some subset of those operators. Okay. So let's call it let's call those operators with a prime, right? So OJ prime, and J goes from, let's say, 1 to M, where M is less than or equal to N. Okay. So for example, in this case, N is equal to 4, right? And so OJ prime, so O prime, this is a set of maximal set of commuting operators, which means that if you look at the commutator of any 2 operators in this set, that commutator is 0. Okay. So you imagine that you have some set of operators, On, right? out of this set, you pick a certain subset. You take two operators such that their commutator is 0. Okay. Then what you do is you pick all such pairs, right? Such that this is true for all j and k, right, in that set. Okay. So as an example, let's say we start with our operators for a two-dimensional potential well like this. This is our initial set of operators. Okay. The curly braces, when you write curly braces, it means that you're talking about a set of objects. Okay. So this is a set of operators, OI 1, 2, 3, 4. Now let's say you pick any one operator. Let's say you pick X. Then let's say we have to find an operator such that it commutes with X. Okay. So some value of this J. Now which operator commutes with X? Y commutes with X. Right? So X and Y commute with each other. Now we have to find a third operator. We want to see, is there a third operator which commutes with both X and Y? Okay. Right? Is that right? No, there is a third operator which commutes with both of these actually. What is that third operator? You can construct that operator by taking a combination of these momentum operators. Okay. So this thing is also going to be 0. So you have this set of operators x, y, and px square, py square. Now, you can prove this, right? What is x comma px square? Using that that same formula, it's minus 2px, right? Okay, so no, it doesn't commute. My mistake. So the only two operators we are left with which commute, right? Our complete set of commuting operators is what? It's x and y. This is one complete set of commuting operators. But there is another complete set of commuting operators. Which one is that? Which is px and py, right? So we can choose either one of these sets, right? We choose any one of these sets, okay? So choose any one complete set of commuting operators. Then find the eigenstates of the operators in that set. Okay. So now we have to find the eigenstates. So what are the eigenstates? So let's say we pick our position operators. So we'll call this CSCO1 and this is CSCO2. So for CSCO1, what are the eigenstates? Right? It's just this ket x and ket y. We are working in the position representation. If we choose CSCO2, then what will be the eigenstates? Working in the position representation again. So we have to ask what is in the position representation, what is the momentum? So what is the momentum operator in the position representation? Anybody?
Minus H bar rho.
Right? So we have to ask what are the eigenstates of this operator. So the eigenstates of this operator will satisfy this equation, right? So what will be the corresponding solution for this? It will be this thing. So this eigenstate, let me write it and let me expand this in a ket, in a basis of position eigenstate. Okay. So I can write it as psi of px ket x dx. Okay. If you insert this back into the expression, what do you get? You get p hat integral p hat psi of px acting on x hat dx is equal to the number p, right? The eigenvalue p times psi of p x hat dx. So if you equate both of these both sides of this, what do you get? You get this. P acting on psi of p is equal to the eigenvalue p psi of p. Okay. Now, I mean, in your normal classes, what would happen is you would just go from here to here. You would say, okay, this is your operator and this is the eigenvalue equation, right? So I'm just following the slightly more longer but the correct path, which is to, remember that this is not the state, this is just the component. So this will have a simple solution. If I look at this, what is this? D of psi p x is equal to some value p psi p x. What will be the solution of this? This will give me psi of px is equal to some constant times exponent of minus I by h bar px. Right? So when I'm in the position representation, my momentum eigenstates are plane waves. Okay? This is a plane wave, right? So if I look at this complete set of commuting operators and I ask what are the eigenstates? Well, the eigenstates are these eigenstates which I've just written down. One will be this eigenstate, p of x ket, and the other will be, let's say, p of y ket. So what is p of x ket? P of x ket is the psi of p for x. And this is the same thing, psi of p for y. Now, once you have a complete set of commuting operators, you find the eigenstates of the operators in that step. Then you can write down any state for any state in your Hilbert space. You can expand this state, you can write this state in terms of that, in terms of the eigenstates of those complete set of operators. So for example, I can write any state in the position representation. I can write it like this. But I can also write down the same thing in the momentum representation. Right? So this is the position representation. This is the momentum representation. Right? Now the question is, can you write down something like, let's say, instead of psi, let's say phi xpx, cat x, cat px, dx, dpx. Is this allowed?
No, sir.
No. Right? Why is that? Because x and p, they form a non-commuting basis, right? They are eigenstates of non-commuting operators. Okay. So now we are in the position representation. Okay. So this is how we write down our states. Now the question is, what about our Schrodinger equation? So we have to ask, how do we write down our Schrodinger equation for this two-dimensional system? Okay. So for 1D, what did we do? We wrote down the Schrodinger equation, right? We said that this is the Schrodinger equation. H psi is equal to IH bar d by dt of psi. This is the general time-dependent Schrodinger equation. And if you have a state in which the time dependence can be, if the state can be written as a time-dependent part multiplied by a time-independent part, in that case, the Schrodinger equation can be written in this way, where this is a time-dependent state, and this is a time-independent state. So this is the time-independent Schrodinger equation. Now, and what is this H? This H is the Hamiltonian, right? Now this Hamiltonian, what is it? Remember, it's the kinetic energy plus potential energy. What is kinetic energy? P square by 2. So if you look at the kinetic energy in one dimension, it's just px square by 2n, right? In 1D. But we are in 2D. So we have to take the kinetic energy along both the dimensions, right? So we have pxy square, px square and py square. This is really the only difference. What about our potential energy? Well, the potential energy will be some function of both x and y, right? So it will be, if you're in 2D, if you're in 1D, it's just a function of x. If you're in 2D, it will be some function of x and y, right? So these are the classical values of these kinetic and potential terms. The corresponding operators we can write down in a very simple manner, right? Operator px square by 2m plus operator py square by 2m, which is what? Which is minus h bar square, right? Minus h bar square is the same for both. Minus h bar square by so what is this? This is the kinetic energy operator part of the Hamiltonian. So I can also write it as hk, right? So now let us set potential to 0. Okay. So that means we have a free particle. So we have a free particle. Let's see what the eigenstates of the Hamiltonian are. So then our eigenstates just become hk acting on psi is equal to some e times psi, right? And what happens? This psi is written in terms of the Keck basis, and then the operator acts on the psi component, right? And this can be written as hk acting on psi of xy is equal to e of psi of x. So this is the form that you are familiar with, right? What does this become? This becomes minus h bar square by 2m, okay, d by dx square psi plus d by dy square psi is equal to e times psi. So this is the Schrodinger equation for a free particle in 2 dimensions. Is this okay? Should I go back, clarify something?
Excuse me, sir.
Yeah,
Sir, but in this equation, the psi depends on x and y both, right?
yeah,
Okay.
right. So this is a partial derivative. You're right. Is that what you were trying to tell me?
Yes, sir. Yes, sir.
Okay, thank you. So these should be partial derivatives, right? Same thing here also. And here. Okay. So this is our Schrodinger equation for a free 2-dimensional particle. Okay. And what will be the solutions of the Schrodinger of this equation? The solutions will be, anybody? Any guesses? The solutions will be of the form some constant times exponent I k dot r or k dot x. What is x? This is the vector x, which is x and y. What is k? Kx, ky. And what is the relationship between k and this e? This e is the eigenvalue, right? So the relationship is the same relationship that we have seen before. That the momentum of the state, now the momentum becomes a vector, right? It's h bar k. And what is the energy? The energy is p square by 2m. So h bar square k square by 2. Right? So these are the energy eigenvalues. for a free particle. And now, but the question is, what is there any restriction on the values that this k can take, right? Kx and ky, can they be any arbitrary numbers? So if the potential is 0, right, then kx and ky, there is no restriction on them. They are just arbitrary real numbers. Okay. But if your potential is not 0, right, then your wave function will have some sort of boundary condition, for example. In that, and that those boundary conditions will result in a restriction on what are the allowed possible values of x and y, kx and ky. So for example, for 1D potential well, right, what happens?
Excuse me, sir.
Yes.
Sir, is a second order differential equation. It has a two solution.
Uh-huh.
Yes, sir.
Okay.
Yes, sir.
Okay, is that fine? So for 1D, what happens is our k values, right? There's only one k, so I'll just write it as k. K becomes quantized, right? Where n is equal to 1 to infinity, right? What will happen for 2D? Right? For 2D, so in 2D, let's say that we have x and y, and now we have to ask what is our potential. So again, let us look at the simple example of a square potential or a rectangular potential. Okay, square or rectangular, it doesn't matter. So basically, you have a box whose width is Ly, whose, you know, in one direction is Ly, and in another direction it is Lx. Okay. So now we are asking for solutions of our differential equation, and what are the values of x of the potential in this region inside the box. We can say v is equal to 0. Okay. Outside the box, v is equal to infinity. So this is our infinite potential well. Just 1 minute, okay? 1 second, please. Sorry. Okay, my apologies. So one of the aspects of living at home is that you have to deal with all kinds of domestic issues. So right now somebody has come to fix some electrical equipment, so I have to go for that. But I'll finish this class first, right? We're almost done with this. So we are asking about the solutions of this equation, right? And the solutions will be the same. The only difference is now that you have two values of k. So you'll have kx n, which will be what? Which will be n pi over Lx, right? So this is your equation for a standing wave. And same thing for Ly, right? But this is the important thing to remember, is that in general, your k value in the x and y directions, they will not necessarily be the same, right? So in the x direction, for example, you could be in the n is equal to 1 state, and in the y direction you could be in the m is equal to 2 state. So your states are of the form psi mn xy, where, so I should put m comma n because it's not the product mn, where mn are the whole numbers, right? And what will be the general form of the solution? Psi mn xy So for simplicity, what we will do is we will take our box and we will move it so that one corner of the box is at the origin and the other corner. So we'll put one corner of the box at the origin of our coordinate system. So if we do this, then we can write down our states in a very simple manner. Root 2 by Lx, okay, times root 2 by Ly times sine of n pi x over Lx times sine of m pi y over Ly. You can call it psi nm. So this is your solution for the Schrodinger equation with an infinite rectangular well in 2 dimensions. Right? And what is this? This can also be written as a product of what? This is a product of psi of nx and psi of my, where psi of nx and psi of my individually, they are the solutions of the one-dimensional Schrodinger equation. Right? So in this case, the problem is very simple because there is no coupling in the xy direction. The xy components, there is no term in the potential, for example, of the form xy. If there was, then you would not be able to write down such a simple product state. Okay. So next, in the next class, we will talk about separation of variables. And the thing is that we have talked about 2 dimensions in Cartesian coordinates. So tomorrow we'll talk about it in polar coordinates also and see what happens. And then we'll also talk about density of states. We'll see what this means. Okay. So are there any questions?
Sir, can we write this as similarly for any dimension?
Absolutely.
Okay, sir.
Yeah, right. Because there's nothing, I mean, the structure is the same, right?
Okay, sir. Okay.
So for 3 dimensions, you just get one more factor of, right?
Yes, sir.
But the thing is that in more than one dimension, you can have different coordinate systems. So you can have in 2 dimensions, you can have a polar coordinate system instead of just a Cartesian system. So in the polar case, then you will get a different decomposition. So for example, you can ask, what if your potential well is circular instead of square? Right? What if the boundary of this potential well is a circle? So in that case, your problem has circular symmetry. So you should use a coordinate system which is adapted to the symmetry of your problem. And there you will, get you will not get such a simple product state. You will get some more complications. Okay, so I'm going to end it here now.